So we're going to look at the principles of sterilization of surgical instruments. And as a matter of fact, we're going to just cover sterilization and disinfection, decontamination on the whole, and the principles involved in all of that. So I think a good place to start is with some of the definitions. So we'll look at the definition of decontamination. So decontamination simply involves reducing or eliminating microorganisms from instruments for their safe use in surgery. And disinfection refers to the elimination of most microorganisms from the surface of an inanimate object. And this is with the exception of bacterial spores. High-level disinfectants, however, can kill spores with prolonged exposure. And then we have antiseptics. So antisepsis or antiseptics referred to the elimination of most of the microorganisms on the surface of living tissue and skin. These are germicides. And so it is very similar to disinfection, except it is for the skin. And sterilization is a process that destroys or eliminates all forms of microbial life, including spores. And that is the part of this that we're going to focus on today, right? The microorganisms that are involved in the disinfection and sterilization process, these range from prions to bacterial spores, mycobacteria, small viruses or non-lipid viruses, fungi, vegetative bacteria, and large or medium-sized and lipid viruses. And they have increasing levels of resistance along this spectrum. So what this is to say is that the medium-sized viruses, fungi, and vegetative bacteria have a low level of resistance to disinfection and sterilization processes. But small viruses, mycobacteria, have an intermediate to high level of resistance. Bacterial spores, on the other hand, are very highly resistant to disinfection. And to get rid of bacterial spores, we need sterilization. And of course, for prions, that requires special prion reprocessing. So sterilization is essentially able to take care of all of the organisms along the spectrum up to and including bacterial spores. So when we approach this topic, it's very important to keep in mind the Spaulding scheme. So the Spaulding scheme is a classification of instruments based on the degree of risk of infection involved with their use. So these instruments could be classified as critical, semi-critical, or non-critical instruments. So the critical instruments are those which pose a high risk of infection if they become contaminated. And what these instruments are is that these are our surgical instruments used in the operating theater, as well as implants and catheters. And these catheters refer especially to intravenous catheters. Semi-critical instruments, these refer to medical devices that have contact with the mucous membranes or non-intact skin. So these are usually your scopes. So your colonoscopes, your endoscopes, your laryngoscopes, bronchoscopes, and so on and so forth. And the non-critical instruments are those which come into contact with intact skin. And these are the general everyday things that we see on the ward, things like bedpans and furniture within the healthcare setup. So what is important to note from this Spaulding scheme is that the Spaulding scheme guides us and tells us what level of of disinfection is required. And so critical items, therefore, need to be sterilized, while semi-critical items require high-level disinfection, and non-critical items require low-level disinfection. And an example of this is that, for example, a critical item might be a needle holder on artery forceps, and that requires sterilization in an autoclave. A semi-critical item like an endoscope or a laryngoscope requires high-level disinfection, and that may be achieved with peracetic acid at a 2% concentration. Non-critical items, for example, let's say a bedpan requires low-level disinfection. So you might be able to achieve this with soap, water, and alcohol solutions. Yeah. So this is the basis of the principles involved in sterilization. So there are a number of methods of sterilization, and we can classify them as either physical methods or chemical methods. And these physical methods we can then further classify as either thermal or heat methods, radiation methods, or filtration methods. Yeah. Now, these physical methods can also be classified as either high temperature or low temperature as well. And then we can have a miscellaneous group on the side as well. So those are two ways to classify the physical methods of sterilization. And then, of course, the other method, aside from physical methods, are chemical methods. And these chemical methods, these can be gaseous, or these can be in liquid or plasma form. Yeah. So we will come to those eventually, but we're going to start with the physical methods of sterilization because this is the most common type that is encountered in the healthcare setup. And the first one is heat sterilization. Now, heat sterilization can then be further subdivided into dry heat and moist heat. And moist heat refers to steam. And what this does is that it destroys bacterial endotoxins. Just to backtrack a little bit, the radiation methods, those serve to cause ionization of nucleic acids, leading to the destruction of those nucleic acids and ultimately death of the microorganisms. And the filtration methods, those actually don't kill microorganisms, those actually just remove microorganisms. And the chemical methods, especially ethylene oxide, works by alkylation of the phospholipid chains, and it leads to disruption of bacterial cell membranes and ultimately death of these microorganisms. Right. So a good place to start is with the heat methods of sterilization. So we can start with moist heat or steam sterilization, and this is the most widely used type of sterilization. Basically, you have saturated steam under pressure in an autoclave. It is both microbicidal and sporicidal, meaning that it kills bacterial spores as well. And it can be done in two ways. And the conventional way is what is done in the commercial autoclave in CSPD, is that it keeps the instruments at 121 degrees Celsius for 30 minutes, right? So 121 for 30 minutes. And then there's flash steam sterilization, which keeps it at 132 for 4 minutes. Some of the advantages of this type of sterilization is that one, it is non-toxic, it is inexpensive, it penetrates the packages in which the instruments are wrapped, and there's a rapid cycle time. Yeah. The flash steam sterilization is very often used in the operating theater itself. For example, if a critical instrument falls on the floor and it needs to be re-sterilized because it's the only instrument available, then you can put it in the flash steam sterilizer in that autoclave at 132 degrees for 4 minutes, and it will serve to sterilize the instrument. One of the disadvantages of steam sterilization is that the materials must be heat resistant. So we can only really use heat methods for heat resistant materials. Yeah. One of the other issues is that wet instruments can rust under these conditions. This is why most of the instruments are made of aluminum and stainless steel, so they're less likely to rust. They are put into these vats. They're called autoclaves. They look like a very large pressure pot, sometimes like an oven. And they work in one of two ways. So we have the gravity displacement type and the high speed pre-vacuum type. And the gravity displacement type basically pushes steam in from the sides or from the top and then forces the air out of the bottom. So there's a top to bottom sort of flow. In the high speed pre-vacuum type, there's an ejector which sucks air out, which allows for nearly instantaneous steam penetration. All right. Flash steam is one of the ones that I alluded to earlier, where you put the instrument in there for 132 degrees for 3 to 4 minutes, and it is done under pressure as well, 27 to 28 pounds of pressure. One of the issues here is that the item doesn't need to be packaged, and that there may be insufficient time to sterilize. Because of the absence of a protective packaging, one of the concerns is that there's possible recontamination of the instrument during transport. And sometimes if the instrument is too hot and it's used too soon, it can cause burns to the patient. Yeah. The next method is dry heat. And dry heat was the very first method of sterilization. And this is used for instruments that can be damaged by moist heat, for example, steel. And it's thought to act by oxidation of the cell constituents. Again, one of the advantages is that it is non-toxic, it's not harmful to the environment, it's less expensive, and it penetrates the materials, and of course it's non-corrosive. The disadvantage, most obviously, is that it is very time consuming. It takes more than 2 hours to actually sterilize these instruments, and it uses very high temperatures of 160 to 180 degrees Celsius. And these types of temperatures are not suitable for most instruments. Most instruments will degrade under these temperatures. So it's only used for the most heat resistant instruments. Yeah. So just a second, we'll be looking at some more of the dry heat approaches. Yeah. So steam under pressure is an autoclave, right? The things that are mostly used for dry heat sterilization, we use it for powders. So it's very good for powdered antibiotics, for example, or cellulose or ink. The packaging that is used as well must be able to withstand these high temperatures. Yeah. So both of these, your moist heat and dry heat, types of high temperature sterilization. And then we have low temperature sterilization, and of these, I want to start with the physical methods. So one of the physical methods here is ionizing radiation. And what this is that it uses mostly gamma rays. And these gamma rays are generated by cobalt-60. Now, ionizing radiation is used in large-scale sterilization. It is not approved for use in healthcare facilities. Yeah, so it's used for mass sterilization of things like syringes, um, needles, catheters, and so forth. Microwave radiation can also be used. The way it works is by creating vibration of the water molecules, and that friction is what generates heat. It inactivates bacteria, mycobacteria, viruses, usually within 1 to 5 minutes, but it must be used on instruments that are not susceptible to melting. Yeah. One of the other methods of sterilization is, of course, the filtration methods. Yeah. So these filtration methods, these don't actually destroy microorganisms. Yeah. And there's two types. There's depth filters, and then there are membrane filters. And what they basically do is that they push substances through these filters, and they filter out the microorganisms. They're used for certain biologic products, for air, for gases which are being supplied to aseptic areas, and they're used for heat sensitive injections as well. And again, they're mostly used in industry. They're not so applicable to the hospital setting itself. Yeah. Going over to chemical sterilization methods, one of the most common used is ethylene oxide. And ethylene oxide is a colorless, odorless, and flammable gas. So it's but it is quite toxic, and that's one of the issues with ethylene oxide. Yeah. It works by causing alkylation of DNA, and it is usually applied at a temperature of 36 to 67 degrees Celsius, with a humidity of 40 to 80%, with an exposure time of 1 to 6 hours. Some of the advantages is that it sterilizes heat-sensitive equipment and moisture-sensitive equipment, and it's able to penetrate the packaging, and it's quite easy and simple to operate. Disadvantages is that it takes a long time. Very often it has potential hazards to the central nervous system and the eyes. It's flammable as well as toxic, as I mentioned before, and it is also carcinogenic. And once the process of sterilization is over, the equipment needs adequate aeration time to remove any residual ethylene oxide. One of the other gases that is very often used is a hydrogen peroxide gas plasma. It is thought to be a fourth state of matter, this plasma. It's a new technology, uses hydrogen peroxide concentrations of 35 all the way up to 90% at a temperature 37 to 44 degrees Celsius, with a cycle time of about 75 minutes. It is advantageous because there's no need for aeration afterwards. Its byproducts are non-toxic, and it has a short cycle time, 75 minutes, not like 1 to 6 hours like ethylene oxide. One of the disadvantages is that the objects that you put there, they have to be dry, and it is sometimes irritable to the skin, and it doesn't penetrate as well. as ethylene oxide. So ethylene oxide is used still more often. Ethylene oxide can be used, for example, if you have a mesh that you're going to implant, falls on the floor or something, and uh, you need to sterilize it. It's good for that purpose because mesh is not it's not heat resistant, nor is it moisture resistant. And dry heat would those temperatures would be too high. So it needs a low temperature, low moisture means of sterilization. And so gas sterilization is the most appropriate method to use for something like mesh. Yeah. There's also formaldehyde steam, which is used in the UK and the European Union. And these keep formalin that is vaporized into a gas, pushed into a sterilization chamber at about 70 to 75 degrees Celsius. And it has a short cycle time, and it's a relatively low cost solution. One of the disadvantages is that it is less penetrating than ethylene oxide, and it's a mutagen and also a potential carcinogen. And it is actually not approved by the FDA for use in healthcare facilities. And another gas approach is ozone. So as we know, ozone, O3, is a powerful oxidant, but it uses a long cycle length of about 4 hours. Temperatures need to be about 30 to 35 degrees Celsius, and it can be used for things like stainless steel, titanium, polypropylene, and it is non-toxic. There are no toxic emissions from it. There's no residue. It uses a low temperature, and there's no need for handling of anything of the sort. Yeah. So that's an overview of some of the main methods of sterilization. Now, when an instrument, for example, falls onto the floor or becomes entangled in some sort of a mess, when a critical instrument becomes contaminated for some reason or the other, a number of steps need to be taken before we can get that instrument into sterilization. And the process starts when there's contamination of the instrument. And so the first thing that needs to be done is decontamination. So the instrument should be sent to the sterile processing unit where it will be decontaminated. So usually gauze sponge moistened with water and with disinfectants is used to remove any debris, dirt, blood, etc. And it is in that decontamination area where those soil items are decontaminated and cleaned. Yeah. So it's actually mentioned in the earlier part of the presentation here, where decontamination involves cleaning, disinfection, and sterilization. So the cleaning is the removal of any visible material from the surface of the object, manually or mechanically. It uses water and detergents, soapy detergents, or sometimes enzymatic products as well. And that is a very essential step. Once that is done, we can use disinfectants, and then the instrument is then packaged. Yeah, it is then placed into these packages where before being placed into the autoclave, for example. So they're placed into the autoclave, and then it's set. And once it is complete, they're then removed and the strips are checked. Once the strips change color, then that is confirmation that sterilization has taken place. Yeah. Now, the facilities that are available for sterilization are important. So we're going to talk about those a little bit now. The central processing area should have a decontamination area, a packaging area, a sterilization area, and then a storage area. So when an instrument goes for sterilization, those are the 4 steps that need to be undertaken: decontamination, packaging, sterilization, and then storage. The areas must have appropriate airflow pattern, that is negative pressure. So air should be pushed in and sucked out. The sterilization area itself should be a limited access area with a controlled temperature, and the floors and walls of the area should be able to withstand any of the chemical agents being used. So the entire sterilization process first involves cleaning of the instrument. The rigid containers or the instruments are opened and disassembled if possible. They're cleaned completely, and then they are loaded into the sterilizer, which allows for proper circulation of the sterilant. The sterilization process should then be monitored, and then following sterilization, the instruments should be handled using an aseptic technique, and the sterile instruments should be packaged and appropriately and stored away from contaminated surfaces. The aim of these sterilization practices is multifold and involve a few key things. Firstly, the healthcare personnel should perform most of the cleaning and disinfection and sterilization in the central processing department. It is meant to protect patients and minimize the risk to staff. It's all about infection prevention here. The other thing is that it is meant to preserve the value of the items being reprocessed. So you don't have to throw these items away. And these sterilization processes should be consistent, they should be monitored, the operator should be competent, and of course, the process needs to be monitored by biological indicators overall. Yeah. In terms of the factors which affect the efficacy of sterilization, of course, if the cleaning process is not properly done, then that leads to some problems because there's a higher bioburden, a higher protein load, and a higher salt concentration, and that will decrease the efficacy of sterilization. The natural bioburden of a used surgical device is about 1 to 1,000 organisms, and that is substantially below the number of spores that are used in biological indicators. Types of pathogens also may affect the efficacy of sterilization. Any residual proteins, any residual salts, biofilm accumulation, which can occur, and that can impair the exposure of the sterilant to the microbial cell. The length of the lumen in the case of instruments that have a lumen, that can impair the amount of sterilant penetrating, and that may require forced flow through the lumen in order to achieve sterilization. The diameter of the lumen also affects it. Again, the smaller the diameter, the greater the impairment of the penetration of the sterilant, and again, it may require forced flow through the lumen to achieve sterilization. The design of the device as well as its construction can also affect the quality of and the efficacy of sterilization. If there are issues with screws and hinges, that can affect sterilization efficacy. So maintenance of the equipment is of utmost importance in this entire process. Yeah. So some of the key things to remember from this is that is the differences between disinfection, antisepsis, and sterilization. Understanding that disinfection refers to inanimate objects and surfaces, and antisepsis refers to living tissue, and sterilization refers to the elimination of all microorganisms from the surface of an instrument. Understanding the Spaulding classification, remember, instruments are either critical, semi-critical, or non-critical. Understanding that the critical items require sterilization, the non-critical items require low-level disinfection, and the semi-critical items require high-level disinfection. That the methods of sterilization can be either physical or chemical, or they could be high temperature or low temperature. Physical methods, heat, which can be dry heat or moist heat, radiation, which can include gamma rays, UV light, ozone, sorry, not ozone, and these are generated from cobalt-60. The filtration methods, which aren't really that important to the hospital setting. Chemical methods, which primarily employ the use of ethylene oxide, hydrogen peroxide gas, plasma, ozone, and so on. So that's a summary up until now. When it comes to semi-critical items, for example, the scopes, then decontamination of those requires a different approach. And what the agents that we use for that are different as a result. So I'm going to touch on that a little bit here as well. Yeah. So let me get on to the semi-critical items. Right. So these are items which need to be free of all microorganisms with the exception of bacterial spores. And these are instruments which will be in contact with mucous membranes or non-intact skin. There's a lot of things that we can use. Most often we can use glutaraldehyde, or we can use peracetic acid. There's also some other things like hydrogen peroxide and peracetic acid, a combination of those, hypochlorite, which is free chlorine, essentially. There's glutaraldehyde and isopropanol, lots of different things. And some of the semi-critical instruments, things like speculums, endoscopes, tonometers, endocavitary probes, your respiratory therapy equipment, anesthesia equipment. So one of the methods used is of course glutaraldehyde, as was mentioned. It's also called Sidex, and this is done by immersion. The instruments are immersed, and there is a test strip that is used which will tell you when the instrument has reached an adequate level of decontamination. Peracetic acid is used as well, 2%, for these endoscopes especially. Now, peracetic acid used at 20% may actually be used to achieve sterilization. When it comes to non-critical objects or non-critical instruments, those are with things which are intact with skin but not mucous membranes, and those require low-level disinfection. Now, this is important as well when it comes to infection prevention and control, because it's these things, the pans and sheets and stools and so forth, which harbor certain pathogens. One of those is MRSA, which can survive on surfaces from anywhere from 7 days to 7 months. We have vancomycin resistant enterococci, which can survive on surfaces from anywhere from 5 days to 4 months. Acinetobacter, Clostridium difficile, HIV, which can survive on surfaces from anywhere from minutes to hours. Yeah. What we use most often here are liquid disinfectants. So we can use alcohol, so ethyl alcohol or isopropyl alcohol at a concentration of at least 70%, all the way up to 90%, or we can use chlorine, bleach, right? Sodium hypochlorite, which at a concentration of 100 parts per million. Yeah. Accelerated hydrogen peroxide at 0.5 or 1.4% can also be used. So the way this is done is that the surfaces must be cleaned first, and there must be physical removal of any grease, soil, hair, all of these things, and the agents must be applied and allowed adequate contact time. Yeah. Some of the other things that we have to keep in mind, things like blood and bodily fluid spills, those must be promptly cleaned and decontaminated. Appropriate PPE must be used. Spills should be cleaned using a dilute bleach solution, and some sort of a hospital disinfectant. Yeah. So that's just a little bit of additional stuff at the end there, and that should be all we have for this.